All right, welcome back. And let's just dive right into an example here. Sam's going to build a computer. He has the choice of computer chips from 2 brands, a hard drive from 4 brands, memory from 3, and an accessory bundle from 5 different local stores. So how many different ways can Sam build this computer? How many different ways can Sam build a computer, right? Well, this is a classic scenario, in my opinion, where I would look at, if I wanted to list out the sample points, this is a tree diagram is perfect for something like this, just to make sure we don't miss any sample points, right? He has a choice of chips from 2 different brands, right? So for the computer chips part, he has 2 options, right? So let's just say there's option. Well, we don't even need to, necessarily name them because I'm just gonna put a sample point here, real quick. So there's 2 options there, right? Now a hard drive from 4. So for each of these, he could have 4 different hard drives, right? So for the hard drive, you've got 4 branches that can go off of each of these, because it could be this hard drive, 1, 2, 3, or 4. Or here, it could be any of those same 4 as well with this computer chip. Memory from 3. It appears that maybe I didn't leave myself enough room here. So I've got memory from 3 different options. So there's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then we can repeat that down here. We'll have 3 branches for each of these here. Let's see if we can't give ourselves some more room. Let me restart this bottom side here and give myself some more space. There we go. So we've got 4 spots to start with. More room than that, huh? Three, 4. Okay, so what do we have for memory? 3 options for each. So there's 1, 2, 3, 1, 2, 3, and then we have 1, 2, 3, 1, 2, 3. Good. And then lastly, an accessory bundle from 5 local stores. Oh boy, accessories. Let's try that again. Let me reset my battery here on the stylus, unfortunately. So for each of these green dots, we're going to have 5 options. Each of these green dots are going to have 5 options. So while this is really nice in organizing our work and making sure we don't get we don't miss anything, so we can see that this tree gets very large very fast, because for each of these, we're going to need 5. We should have 5 branches coming off each of these. We would have 5 branches coming off each of these. So we're going to have 5 branches coming off that. 5, 5, 5, 5, 5 branches. We definitely didn't leave ourselves enough room to make this tree diagram. It is actually quite large, but we wouldn't be missing anything, which is nice. So, how many total ways are there? Well, we got to add up our 5s, right? We need to add up our 5s. How many fives do we have, right? Well, that would be 5 times the number of green dots that we have. How many green dots do we have? Well, that would be 3 times the number of blue dots that we have over here under the HD category, hard drive category. Well, that would be 4 times the number of chips that we can choose from, right? So at this stage, you have 2 options right here. 2 options right there, okay? And then for each of those, you have 4 hard drives to choose from. So for each of those, you would have 4 hard drives to choose from. There are 8 blue dots at this second level branch. But for each of those, you have, 3 memory chips to choose from. So for each of these blue dots, we would have 3. And then for each of those memory chips, we would have 5 different accessory bundles we can get at. So what do we have here in terms of the number? We would have 2 times 4. There's 8 blue dots at this second stage. And then for each of those, we have 3 memories. So we'd have 8 times 3. 8 times 3 would give us 24 green dots. And for each of those, we would have 5 options to look at. 24 times 5, there is a total of 120. A total of 120. All right. So the idea here is when you're just asked about the number of ways something can occur, but you're not actually concerned with specific elements or listing out the sample points, we can really count the number of ways in a question like this by just multiplying the number of options you have at each stage. This is an example of the multiplication rule. The multiplication rule. Multiplication rule. If an operation can be performed in, we'll say, n1 ways. So an operation could be performed in n1 ways, and if for each of these, if for each of these, a second operation can be performed in n2 ways. And then for each of those, you could do a third operation in n3 ways, so on and so forth. I'll just say etc. The sequence of k operations, can be performed in n1 times n2 times n3, yada, 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 times nk ways. We just multiply the number of ways we can perform each step together. That is our multiplication rule. All right. So let's look at a new fresh example with the multiplication rule in mind. Let's say a customer wishes to buy a cell phone. Customer wishes to buy a cell phone, and they can choose from 5 brands, 5 bill plans, and 4 colors. How many ways can they buy the cell phone? 5 brands, 5 bill plans, and 4 colors. Very quickly, there are 5 ways to choose the brand, then 5 ways to choose your bill plan, and 4 different ways to choose your color. 5 times 5 times 4. Run that through a calculator. 100 different ways. 100 different ways. And there is your multiplication rule. No tree necessary. No tree necessary, right? But this does tie into that tree. I like to see that visual at the start because essentially this would be a tree in the end that would have 100 different branches at that final stage. Be quite large, right? And you can see why we didn't have a good time drawing this tree, because we'd be looking for something that can fit 120 branches. Let's try another example. How many ways are there to order the letters A, B, and C? The letters A, B, and C. All right. Okay. So this is actually a multiplication rule question, even though it looks slightly different, because the stages, if you will, are not as clearly laid out as they were in the previous example. In the last example, you could think of each stage as choosing part of the cell phone package, right? What brand, what build plan, and what color. Here, what are your stages? Well, your stages are what letter comes first. And in the first stage, there are 3 letters to choose from. But in the second stage, you've already used one of these letters. So I can only choose from 2 remaining letters, because you're just ordering these 3. You're ordering A, B, and C here. So you could have ABC, you could have BAC, you could have CBA, yada, 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 right? After the second stage, you've chosen 2. The last stage, there's only one option, right? The third letter is determined based on your first. So we have 3 times 2 times 1, or 6 ways to do this. 6 ways. 6 ways. 6 ways. Operations that fall under this pattern of stages are called a permutation. Permutation. A permutation is an arrangement of all or part of a set of objects. An arrangement of all or part of a set of objects. An arrangement. So how many ways can we arrange these 3 letters? All right. And we have some notation for this. In general, n distinct meaning you can tell the difference between the n objects. N distinct objects can be arranged in n times n minus 1 times n minus 2, yada, 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 all the way down to 2 times 1 different ways. Because, again, once you've used an object, you cannot use it in the next stage in permutations. And so the number of options you have decreases by 1 at each stage. And the notation for this multiplication is n factorial. That is n factorial different ways. N factorial. By convention, by the way, just to be aware of, some of you have probably seen the factorial symbol before, but just in case you haven't, by definition, we take 0 factorial to be 1. And that is important because it is possible to have a 0 factorial show up in a denominator, and we need that to be defined. You could also think of it logically this way. If we're talking about the number of ways of arranging objects, you could say, how many ways are there to arrange 0 objects? And one could maybe make a case that there's 1 way to arrange 0 objects. You don't. Maybe you like that, maybe you don't. If you don't, there's a lot of interesting videos and takes that we can get into later on. If you want to contact me, I have some sources I can reference for you that make a really good case that 0 factorial should be equal to 1, and that is the correct take. But for now, let's go with it. So with this in mind, let's just dive into a couple other quick questions. How about the number of permutations then? So now we're going to add the word permutations. So this is part of a question. When you say permutations, it's how many ways can you arrange these objects? How many permutations are there of the letters A, B, C, and D? The number of permutations of A, B, C, and D is, well, this is just direct to the definition, just 4 factorial. 4 distinct letters, 4 factorial. 4 factorial is 4 times 3 times 2 times 1. 4 times 3 times 2 times 1. 2 times 1 here. That is 24. 4 factorial is 24. Okay, so what if instead we're looking at these 4 letters A, B, C, and D, but we're only just going to take 2? What if we just take 2 letters from the 4? From the 4. Because remember, a permutation is an arrangement of all or part of a set of objects. So let's say our set of objects is these 4 letters, and we're going to take a part of that. So we're going to take 2 letters of the 4. Then how many permutations are there? Okay. Well, let's just think of it in terms of the multiplication rule and how many options you have at each stage. Using the multiplication rule, the first stage you have 4 letters to choose from, right? And then in the second stage you would have 3 letters to pick from, and that's it, right? You don't do the last 2 stages because you're only picking 2 letters. So according to the multiplication rule, this is a quick 2-stage problem. 4 times 3, there are 12 ways. There are 12 ways to do this. All right. Is there a way to relate these permutations of these smaller sets to the larger idea of these of the full set, the factorial? Well, we can see a relationship here on these 12 ways, because 12 is exactly half of 24. But it's not that we're taking 2 from 4 being half the size of this set. It's because 4 factorial, look at 4 factorial over 2 factorial. If we expand the factorials, 4 times 3 times 2 times 1, divided by 2 factorial, which is 2 times 1. 2 times 1, take a look. These are going to cancel. And we're going to get our 4 times 3. We're going to get our 12. We're going to get our 12, okay? So, not is it that we're dividing by 2, but we're dividing by 2 factorial. When you're only taking 2 letters from the 4, you're needing to get rid of, if you will, the last 2 stages, right? And typically in the multiplication rule, when you have the last 2 stages, you'd be multiplying by 2 factorial. So what we do then is we're going to undo that operation, right? The inverse of our multiplication is not subtraction, but it is division. And so we would be dividing by that 2 factorial. We would be dividing by that 2 factorial. Okay? And this does extend generally, and this is associated with Theorem 2.2 in the textbook. And if you go ahead and take a look at the e-text there in Chapter 2, you can find Theorem 2.2 that says the number of permutations of n distinct objects, taken r at a time, is, we use the notation NPR, and that not for National Public Radio, NPR, taken from the total set of n objects, you're choosing r of them, and that would be n factorial divided by n minus r factorial, right? You're dividing by the remainder of steps in the full general multiplication rule that you're not doing. You're undoing that operation from the multiplication rule. NPR. N factorial over n minus r factorial. Let's do one last example directly related to this theorem, and then we'll take a break. 3 awards. 3 awards. Let's say, and we want these to be distinct. So let's say there's an award for teaching, an award for research, and an award for service. So they're different awards. Will be given to a class of 25 graduate students. Given to a class of 25 graduate students. 25 graduate students. Now, if each student can receive at most 1 award, each student can receive at most 1 award, how many possible selections are there? How many possible selections are there? How many possible selections are there? Well, there are 3 awards, and they will be given to a class of 25 students. All right, so essentially, we need to pick 3 students out of these 25, 3 students from the 25 to get the awards. All right, so this is literally just 25 P3. This is 25 factorial over n minus r. So this would be 25 minus 3, the quantity factorial. Not 25 factorial minus 3 factorial, but 25 minus 3 means in the denominator we're going to have a 22 factorial. 22 factorial, okay? And the nice thing about working with these factorials and writing this out is the multiplication here is actually way simpler if you reduce this down first, right? Don't go ahead and punch in 25 factorial in the calculator and then divide by 22 factorial. You could try, but depending on the calculator you have, you might have some overload because 25 factorial is huge. Instead, let's look at this relationship. What is 25 factorial? Well, it's 25 times 24 times 23, and then we'd get to 22, and 22 from there on out, that's just 22 factorial, right? All the way down to 1. And then here we have 22 factorial. So we can actually divide out and reduce out the 22 factorial, so this is just left with 25 times 24 times 23, which is very straightforward to punch into a calculator at this point. 13,800 would be the final result. And I really like writing these factorials out and reducing down the multiplication because this really hammers in the idea of how these permutations really relate and come from the multiplication rule. Because when you get to this stage right there, choosing 3 awards, this is a multiplication rule question that has 3 stages. So you can think of it in either way. You could think of it as a permutation, 25P3, or you can think of it as a 3-stage multiplication rule question where you choose 1 student first. There's 25 students to pick from. Once that student has an award, they can only get 1 award. So the next stage, there's only 24 left. Then there's only 23 left. And you've chosen all 3 awards and you're done. This is a good place for us to pause. Let's take a break, grab a snack, go to the bathroom, see if we have any questions, post those in the discussion thread below. And then we will be back for more on counting sample points. I'll see you in the next video.